And here's another example more recently from the 2011 Tohoku-oki earthquake in Japan. Again, the published literature has different models, all kinds of different ruptures. So I'm going to get a little mathy here because I figure this is an audience that might actually enjoy math. So let's think about a simple linear problem. You know, your data equals some G matrix times a vector of model parameters M. And of course, there's lots of ways to solve this. The most obvious one is least squares. But remember, if the problem is ill-posed, we can't evaluate the inverse of G. So normally what we do is we use regularized optimization. So we pick some regularization scheme, and then the inverse finds a solution that fits the data and fits that regularization scheme. And of course, the choice of regularization is often based on what's mathematically convenient to get the problem to work from a numerical standpoint. It's not usually based on the physics of the problem. And of course, choice of regularizations can have enormous effects on the resulting solution. That's what we just saw in the last two slides when we looked at the different slip models for Tohoku and Landau's. You change your regularization, you get a whole different answer from what's possibly a very large, underdetermined space of possible solutions. But with Bayesian inference, really what your solution is, it's the ensemble of all plausible models. It's going to be a probability density function, a PDF, that describes the relative plausibility of all source models given your data and given whatever constraints you want to put on the problem. And what we're going to see throughout the rest of this talk is when you go to evaluate these solutions, G inverse is not going to show up. And thus, you're never going to have to regularize the problem just so that you can evaluate the solution. You are free to put in any kind of regularization or constraints that you like, but you never have to do it just to be able to evaluate the solution to the problem. So let the motto of this talk be embrace uncertainty. When faced with a lack of model resolution, really the answer that you want to the inverse problem is to identify the ensemble of all plausible values for your model parameters. Because if there's more than one model that fits the data and that fits your constraints on what the model could be, it's not really helpful to just pick one model. And plausible models, when I say plausible, what I really mean by that is models that fit the data and that agree with whatever prior assumptions you make about the model parameters. And in the literature, they often talk about the prior in terms of being what you believe the likely values for your model parameters are before you go out and try and fit the data. But really, the more intuitive way to think about it is just to say the prior is the place where you can put in whatever constraints you want to use. And you can make those constraints be based on the physics of the process you are trying to model. Again, usually you don't have to do anything to make the problem numerically stable. And by being explicit about what your assumptions are based on these laws of physics, and I am assuming this and assuming that, that's really a good thing. That makes your solution opener and easier to interpret. So I would say making explicit assumptions is a feature, not a bug of Bayesian analysis. Okay, so Bayesian inference for inverse problems. Because really today, you can use Bayesian inference for anything, but today we're just going to talk about inverse problems. And this goes all the way back to Bayes' theorem in 1763. So what Bayes' theorem says is that there is a posterior PDF that describes the relative plausibility of all possible values for all of your model parameters. And it's proportional to the product of the probability that you assign to your model parameters. Lorraine just said I cut out. Can people hear me now? Oops. Am I hearable now? I'm talking? Okay, good. We're going to keep going. Okay, oh, back up. We are backing up a slide. Okay, so embrace uncertainty. So when you have an underdetermined inverse problem, what you really want is to find all of the solutions that fit the problem, all the plausible models that fit your data, because if there's more than one model that fits your data, we need to think about both of those models, or all of those models. And by plausible, what we mean are data, are all the possible values for all the model parameters, for all the models that fit your data, but that also satisfy all of your prior assumptions. And what do we mean by prior assumptions? Well, in the literature, you usually see it listed as, or referred to as, what you believe the likely values of your model parameters are before you actually look at the data for the particular thing that you're trying to model. But really the more intuitive way to think about it is that the prior is the place where you can put in whatever constraints you want to put on the model parameters. And these, again, these constraints are really just whatever you think is required by the physics of the process you're trying to model. You do not usually have to do anything to make the problem numerically stable. And thus, you'll make just a set of assumptions based on the physics. You write those down explicitly, and making explicit assumptions is really a good thing. It's a feature, not a bug. Okay, so Bayesian inference for inverse problems. You can use Bayesian inference for many different things, but today we're just going to talk about inverse problems. And so we're going to go all the way back to 1763. And what Bayes' theorem says is that there is some PDF called the posterior PDF that describes the relative plausibility of all of your different models, of every possible value for every one of your model parameters. And the vector of model parameters we call theta. And really, that PDF is just going to be proportional to the product of your prior constraints, which is whatever you want them to be, and the product times your data likelihood, where the data likelihood is a metric of the goodness of fit between the forward model with that vector of model parameters and your data. So G of theta is going to be the output of your forward model, D is a vector of data, and C is a covariance matrix. Unfortunately, part of this equation got cut off, but it's the same equation as on the previous slide. So if you can admire the equation that you can no longer see because it's cut off, you'll notice that that the solution to the inverse problem is written in terms of the forward model. It's written in terms of G, not G inverse. So this is where the magic comes in. Since you do not have to evaluate G inverse, we don't care whether the problem is underdetermined. In fact, the only matrix inverse you see here is inverting the covariance matrix. And covariance matrices are by definition symmetric positive definition. And so by definition, they are invertible. So remember, regularization is never required, even for ill-conditioned problems. So here's another checklist of things that make Bayesian analysis useful. Optimization only gives you one solution, but Bayesian analysis gives you the distribution of all plausible solutions. Optimization only converges to one minimum, and then you have to worry, is this the global minimum or is this a local minimum? But with Bayesian analysis, since you're getting the whole ensemble, marginally peak solution spaces are A-OK. Optimization requires regularization, and then you have to decide, how do you choose your regularization? What's physically the right form of regularization? What makes sense based on the physics of the problem? Whereas in Bayesian methods, you're certainly allowed to use regularization, but it's not at all required. In optimization, you often have a limited choice of constraints because maybe the numerics of the problem require you to keep it linear or something. But in Bayesian analysis, you can use whatever kind of constraints you want: linear, non-linear, simple, complex, weird, whatever. When you try and optimize a nonlinear problem, it's often very hard to do an error analysis on the solution. But with Bayesian analysis, since your solution is a PDF, the error analysis is essentially free, right? The average of that PDF is the average solution. The median of that PDF is the median solution. The variance of that PDF is the variance of the solution. The area or volume of that PDF that contains 95% of the density is your 95% confidence interval. And often when you do optimization, there's always issues with how exactly you parameterize a problem, because maybe you get trade-offs between different parameters, and that makes the solution hard to converge. Whereas in many different kinds of samplers that you can use for solving Bayesian problems, the trade-offs are not a problem in terms of estimating the posterior PDF. Okay, so how do you do Bayesian analysis? And I'm going to sort of roughly break it into two categories. So option one is do whatever you want. Pick whatever prior distribution you want, no matter how complex. Pick whatever data likelihood you want. And then you just numerically simulate the posterior PDF by using Monte Carlo simulation. But that can be numerically expensive. Option number two is if you choose your priors wisely, you can get an analytical expression for the posterior PDF. Normally this is done with something called conjugate priors. For example, if for your data likelihood you were to choose a Gaussian distribution, an L2 norm for your misfit, and if you were to choose Gaussian constraints on your model parameters, then your posterior PDF is a Gaussian times a Gaussian, which is a Gaussian, and you can just write that down. So option one is totally generic. It allows you to do whatever you want, but it may require a whole lot of computer power to be able to actually simulate that solution. Option number two can be ridiculously cheap, computationally speaking, but you're going to have to work out the math, which requires some brain power, and also you maybe can't solve the problem exactly how you want to solve it because you're going to have to make choices that lead to an analytical solution. And in the examples that follow, we'll do examples of both. So let's start with the numerical approach. So again, when you say I'm just going to do a numerical answer, you can do whatever you want. So you can choose any metric for your data fit. You can use an L2 norm. You can use the L1 norm, which is the Laplacian norm. You can do any kind of model design. It can be linear, it could be nonlinear. You can use any kind of constraints on your model parameters, linear, nonlinear. And then you just compute the solution through Monte Carlo simulation. But there are some issues with Monte Carlo simulation. Mainly the cost of dimensionality, which means that if you have a big parameter space, it may require infinite computing time to sample the entire solution space. So the theory behind Monte Carlo simulation is like this. Basically, we want to draw samples of our posterior PDF. And then the samples will have all the properties of the posterior PDF. The mean of the samples will be the mean of the posterior PDF. And the variance of the samples will be the variance of the posterior PDF. And the bounds that contain 95% of your samples will be the 95% confidence interval on your posterior PDF. But there is really no such thing as a generic random number generator. I can't just draw samples of some random PDF. There are algorithms for drawing things from a couple of distributions, a uniform distribution, a Gaussian distribution. But otherwise, you're sort of out of luck. Except that there are a bunch of algorithms that allow you to eventually get samples from the thing that you want to draw samples from. And so the way you use Monte Carlo, all the algorithms for Monte Carlo sampling of a generic PDF look about the same. Basically, you draw random samples from something that you do have a random number generator of. So we call this the proposal PDF, and usually it's something like the Gaussian distribution. And then for each of these samples, you decide whether to keep or reject that candidate sample, which in our case is going to be a candidate model because we are sampling the parameter space. And you decide whether to keep or reject it based on basically what its probability is in the thing you're trying to simulate versus the probability of the thing that's generating samples or something like that. And then you go back to step one, you draw another sample, and you decide whether to keep or reject it. You draw another sample, and you decide whether to keep or reject it, and you keep going, and you keep going, and you keep going. But note that not all candidate samples are accepted. In fact, it can take a lot of samples, candidate samples, to effectively, get some tiny fraction of those to be usable samples of the thing you're trying to simulate. And so this can be a really inefficient process. On top of that, there's this thing called a cost of dimensionality. And so here's a picture that I stole off the web. And it's not a great picture because it looks like a grid search rather than sampling a PDF. And we are sampling a PDF. We are generating samples proportional to this probability density function that we're trying to simulate. But what this picture is trying to show is that if you want to have some density of samples in a 1D space, well, you're going to need the square of that number of samples to fill up a 2D space. And you're going to need to the power of 3 of that number of samples to fill up a 3-dimensional space. And so as you go to higher and higher spaces, parameter spaces, you need higher and higher numbers of samples. And so to do a really high-dimensional inverse problem, you're going to need an incredible number of samples to fill that parameter space. And in general, the numerical cost of doing this is the computational time to compute your forward model times the number of samples you need to draw. So if you have a large number of model parameters such that you need a huge number of samples, you better have a fast forward model. Or conversely, if your forward model takes a lot of time to compute, you better be able to write it down in with only a couple of free parameters. And in general, it's the number of parameters that gets you, because it's linear in terms of the computational time, but it goes to the power of the number of unknowns in the problem you're trying to simulate. So when in doubt, go with the least number of free parameters you possibly can. And then it gets worse, sort of, because it's not just that the space is larger as a power of a number of free dimensions. Space gets weirdly shaped as you go into high dimensions. So here's another picture I took from the internet, which is supposed to attempt to visualize what a 7-dimensional cube would look like. And basically the problem is, as the number of dimensions goes higher and higher and higher, almost all the volume ends up in the corners of the cube. So actually trying to find, the meat of the cube is looking for a needle in a haystack. So Monte Carlo simulation can be inefficient to begin with. You need a ton of samples to get to simulate a high-dimensional space, and it can be even more inefficient to draw those samples in the high-dimensional space because it can be really hard to explore that space. That being said, don't be afraid of high-dimensional problems. I mean, we live in an age of lots of computers that are very fast, and so they're all efficient parallel sampling algorithms, and you go to a Beowulf cluster and you split the problem up, and you can draw a whole lot of samples in not a lot of time. So really, you should be warned that high-dimensional problems can be expensive, but that shouldn't scare you off from doing that. You're just going to have to hit it with a lot of computational power. Okay, so let's go through the mechanics of Monte Carlo simulation in some more gory detail, because I want to let you see how this works from beginning to end in an example problem. So basically, every kind of Monte Carlo simulation looks about the same way. You generate a candidate sample, which in our case is going to be a candidate set of values for your model parameters from some proposal PDF, which people usually pick to be a Gaussian. And then you decide whether to keep that sample or reject it. And so in the Metropolis algorithm, which is the granddaddy of all sampling algorithms, which is a random walk, you calculate something called R, which is the ratio of the posterior probability of the proposed sample to the posterior probability of the current sample that you have. If R is greater than 1, you accept the candidate sample. Otherwise, you draw a random number between 0 and 1. If R is greater than the random number, you can keep that sample. Otherwise, you throw out the candidate sample. And so notice that sometimes you always take a candidate model if it's better than the current model you have. But you sometimes also take new models if it's worse than your current model. And what that means is that you're walking through probability space, you find some area of high probability, you take a bunch of samples there, but eventually you're going to jump out of that. And so you don't get stuck in a local maximum, or what you would think of as a local minimum when you're trying to minimize a residual. Eventually you will visit all parts of the parameter space. So again, just writing it down in gory detail, the formula is to take n samples for j equals 1 to n. You calculate a sample from the Gaussian, you calculate R, you pull a random number between 0 and 1, and you decide whether to keep the sample, or if not, you duplicate your current sample. And these are the steps of the Metropolis algorithm. So that brings us to example number 1, an epicenter location problem. This is a toy problem solved numerically. So the steps to doing Bayesian analysis are design a forward model that you're going to stick into your likelihood function, choose prior assumptions to define a prior PDF, and then use Monte Carlo sampling to generate lots of random numbers and eventually fill in the posterior PDF. So this is an example I took from Albert Tarantola merely as an excuse to give you the address of his wonderful website. Where he has lots of, well, he's passed away now, but his website is still alive and well, and it has lots of interesting basic examples of Bayesian analysis. And he also wrote a number of very important books and papers which are worth checking out. So this is an epicenter location problem. So our data, our arrival times, is a bunch of stations located at some x and y coordinates, and they have some uncertainty on those times, sigma. And then we have our model parameter, which is a two-dimensional vector, the x location of the earthquake and the y location of the earthquake. And our forward model is just the, for the travel times, is just the distance between each of the stations and the location divided by 6 kilometers per second. We're pretending these are p-wave arrival times. And then the prior PDF, we're going to say, for some reason we think the earthquake is located between 0 and 10 kilometers in x and y. So we're just going to have a uniform distribution. So our posterior PDF is going to be proportional to the a Gaussian, which is the misfit between the observed arrival times and what's predicted according to that equation above. And then our prior PDF is uniform, so it's between 0 and 10 kilometers, so it's 1 divided by 10 for the x coordinate and 1 divided by 10 for the y coordinate, so 1 over 100, assuming that you're between 0 and 10 kilometers, if otherwise the prior PDF says it's going to be 0. So you take an initial guess location. In this case, I said, let's try 5 kilometers and 5 kilometers. Then I do 50,000 samples. I ran the Metropolis sampler for 50,000 steps, just going through the steps on the previous slide. And this, on the right side, you will see the little black dots are those 50,000 samples. And as you can see, it starts walking off with some determination towards where the actual solution is. And then it draws a whole bunch of samples in that area. The blue triangles are the locations of the stations I used in this game. The pink star is the true location of the epicenter. The black dots are the 50,000 samples, and then the red box is just a box that contains 95% of those samples. So the reason I show this in such gory detail is that I wanted something that you could take home and try out yourself in MATLAB or Mathematica or something like that. And it should just take you a few minutes to code it up and run it. And it'll at least give you experience with, oh yeah, this is how I go do Monte Carlo simulation of a problem. And the first thing you'll discover is that you never actually want to deal with probabilities. They are terrible, they're numerically difficult, they only run between 0 and 1. Rewrite everything using log likelihood so that you have the log of the posterior distribution and the log of the data likelihood, which gets rid of the exponential, the log of the prior, so it's no longer 1 over 100, it's -2 log 10. It's the log of the posterior, which makes it the sum of the log data likelihood and log prior, and then you can rewrite all that way. But seriously, you just take it home, do it in MATLAB, so that you will have seen for yourself how this game is played. And then there are many, many different kinds of samplers out there. Sherman Greenberg's a good reference for understanding the Metropolis algorithm or the projection algorithm. There's Gibbs sampling, there's tempering, there's annealing, there's transitioning, there's all sorts of things. Or you could just build your own. So there is something for everyone out there somewhere. So as a different example, let's look at the Tohoku Oki earthquake. And we're going, this is a big problem, you know, because now this is a finite fault solution. So we're going to solve for two components of slip duration and rupture velocity for each of, hundreds of different locations on a fault. I don't want to go through the details too much, but this is the full-scale kinematic rupture model, which means about 1,000 free parameters. So this is going to be a huge problem. And we're going to use very, very, very broad trials because we want to see what the data resolve and what the data don't resolve. And so basically the idea is, because it's a huge problem, we're going to need a lot of samples. So for 1 to a gazillion, you draw a random source model, you calculate the prior, you run the forward model, you evaluate the posterior, and then you can you hear me? Oh, the sound is intermittent. Oh, the sound is good. Yay! Okay, well, I actually don't have anything to say about the priors. We just chose very broad priors so that, oh, back up another slide? Will do. Okay, so the forward model. I don't want to go through this in too much detail for time or just because it's not that interesting, but this is an example of doing a big problem. So this is the full kinematic rupture parameter. For each of many hundreds of places on the fault plane, we're going to solve for two components of slip, the duration of slip and the rupture velocity. And we're going to use lots of different data. We're going to have GPS offsets, seafloor geodesy, tsunami waveforms, and predictions. And some of this is going to be linear, some of this is going to be nonlinear. It doesn't matter. It just all goes into the mix. And the prior PDFs we're going to choose are going to be very broad, because really this game is to make it in comparison to the various Landor solutions, the various Tohoku solutions we already saw, is what happens if we don't regularize the solution? What is the ensemble of all possible models that satisfy the data and just don't violate any laws of physics? And since this is a huge, very high dimensional, like 1,000-dimensional problem, we're going to need a lot of samples. So for 1 to a gazillion samples, you draw the source model, you assign a prior probability to it, you run your forward model, you calculate the posterior, and over and over and over again. So we ran this in parallel on NASA's Pleiades supercomputer using, my own homebrew parallel sampling algorithm, which I get to show for because this is my webinar. So yay, CatNip is excellent. And by the time this was finished running, we had calculated 50 billion candidate rupture scenarios. So anyway, this is the average slip from all those models that we just calculated. But that's just one slip model, right? So another way to look at it is on the right here, you can see the little purple PDFs that describes the range of possible slips for each of those different patches. Or on the left, what I'm showing is the mean and the uncertainty on the total sum of a long strike slip. So this is just different ways of looking at this 1,000-dimensional PDF. Another way you can look at the 1,000-dimensional PDF is like, let's say you want to know about the source time function of the earthquake. Well, you can calculate the average source time function, but also the 95% credibility interval on the source time function. So red is the mean, and the black dashed lines are the credibility interval. I should mention, in Bayesian literature, they usually refer to it as credibility intervals rather than confidence intervals. I don't know what the source of that is. And because we have uncertainties because we have a whole ensemble of slip models, anything we then calculate from those source models also have uncertainties, right? So this is a distribution. So you don't get, a total amount of slip or slip potency. You get a distribution of slip potency. You don't get a seismic moment. You get a distribution of seismic moments. You don't get a static stress drop. You get a distribution of static stress drops. So, it took an enormous amount of work to calculate this ensemble of solutions, but once you've done it, you have it, and then you can go back and you can analyze it however you like. Okay, so we're at the halfway point. We've beaten to death the issue of how to do numerical simulation. They were both, straightforward inversions, just saying I have some data, I have a forward model, and I want to invert for a set of model parameters. But it turns out you can use Bayesian analysis for even sort of more complex problems than just the inversion itself. Basically, the bigger picture is anything you can do with statistical tests, you can replace with Bayesian solutions or probability logic. So everything that we worry about with chi-squares and f-tests can often be done easier, better with Bayesian tools. So what we're going to talk about now is something that's called model class selection, which basically means what's the best model design. And up until now, every time I've written down Bayes' theorem, I've written it down with a constant proportionality. It's proportional to the data likelihood times the prior. And the constant proportionality is simply because PDFs have to integrate to run, the total probability has to be 1. It's just the integral of the data likelihood and the file, which is a number, a scalar number. But that scalar number turns out to have a lot of significance. And I won't go through the details here. There's a nice discussion of it in this Muto and Beck paper. But that number, that scalar number, the denominator of Bayes' theorem, is the evidence in favor of the model design, or it's also called the marginal likelihood. And it's theoretically a very nice metric that both maximizes the data fit but penalizes for model complexity. So it tells you, is this a good model, or are we overfitting the data, or are we underfitting the data? So here's another example, which gives me an excuse to point you to Tom Minka's website. He also has a lot of interesting little toy problems and examples and introductions to Bayesian analysis. And so this problem he's showing now is, he has a bunch of data and he wants to fit it with a polynomial. What degree polynomial should he fit it? So first he fits it with a straight line, and then a quadratic, and then a cubic, and then degree 4, degree 5, degree 6. On the bottom left is the likelihood. It's the fit to the data, which, of course, as you increase the number of model parameters, you can fit the data better and better and better. So the higher the degree of the polynomial, the more the number of free parameters, the better you'll fit to the data. But the evidence on the bottom right, this would be the denominator in Bayes' theorem, the probability, the goodness, the evidence in favor of this model design, the marginal likelihood for this model design peaks at 3. Cubic is the best model. Things less than a cubic don't fit the data well enough, and things higher than a cubic are too complex, they're overfitting the data. And so that is really a useful little probability to pull out of Bayes' theorem. Which brings us to example number 3, which I will call the ridiculously cheap analytical solution approach. So now we're going to look at things you can calculate analytically rather than having to hit them with a numerical hammer. So whenever you look in the literature about changepoint analysis, you basically see 2 examples in textbooks. One is, did the annual discharge from the Nile River decrease after they built the Aswan Dam? And the other one is, did the annual number of mine disasters decrease after they passed the National Mining Act, National Mine Safety Act? So let's do the Nile discharge problem. And this comes from this 1978 paper by Cobb, and then I'm copying the version of it that was in the Dennison et al. Book. And so the idea is simply this. Let's say that there is a change in at least, changepoint analysis says there was a change in at least one model parameter. So what we're going to do is we're going to fit a mean level to the data, and we're going to see if that mean level of the data changes at some point in time. And so we're going to use Bayes' theorem to compute the probability that the average discharge has changed as a function of time. And then we can also use Bayes' theorem to assess whether any potential change is in fact significant. So this change point detection, basically it's just Bayesian piecewise linear regression. So you have some model, which is just going to be a linear model. It's G times, in the Dennison book they call it beta instead of M, but it's basically D equals G times M. But that matrix changes, and in fact your parameters could change too at some time t that we don't know. And so our goal is to find what would be the best time t to fit the data. Where do we need to have a change in our forward model? So, heuristically, the steps here are, we're going to use a Gaussian likelihood function again. And then we're going to use a prior distribution called a normal inverse gamma distribution. It's a thing. You can look it up on Wikipedia. It just happens to be a handy, numerically easy PDF. And there are reasons why people like to use that particular PDF as a prior for linear regression, and we're not going to get into that now. But then your posterior distribution is going to be a Gaussian times a normal inverse gamma distribution, which is a Gaussian times an inverse gamma distribution. So you have a Gaussian times an inverse gamma, which is a Gaussian times an inverse gamma, which is a Gaussian inverse gamma again. So basically, it's a conjugate prior. You used a normal inverse gamma prior, the posterior distribution is going to be a normal inverse gamma, and that means you can write down an analytical solution for this is what the posterior PDF is, and you can write down an analytical solution for this is what the evidence or the marginal likelihood is. So, this did not get imported well, apparently. But this is the math that is involved, or at least it was originally. Long story short, you plug in Gaussians and inverse gamma distributions, and your solution for what the denominator in Bayes' theorem looks like is this number that's highlighted. And it is, in fact, a number. It's a scalar number that you can just calculate. So for each point in time, you can calculate this number and say, this is the probability at this time that the average discharge from the Nile changed. So you're just fitting an average level, which means your G matrix is just a column of ones, or rather it's a two-column matrix that's all ones in the first column and all zeros in the second column until the break in the piecewise continuous function, and then changes and it's zeros in the first column and ones in the second column. So you're fitting a step, and so for each time t, you just change which row of your matrix changes from swaps from 1, 0 to 0, 1. And you do the inversion again, and you calculate the marginal likelihood again. So on the top here is the data. And as you can see, it's very, very noisy, but it looks like maybe the mean does decrease. But when you go through and you calculate this expression for every point in time, in fact, there's a big spike. There was a very, very definite change point here. That change point occurs in 1898. The Aswan Dam wasn't built until 1902, so it was probably a change in the climate, not the Aswan Dam. Okay. I will keep talking. Let me know if you can hear me again. I am speaking in a monotone. Okay, and we're back. So, where we left off was, so despite the fact that the data is very, very noisy, when you go and do through this analysis, you find that there is clear evidence for change point, and that change point very definitely happened at 1898. But the Aswan Dam wasn't built till 4 years later. Or at least it didn't come online until then. Okay, so final example, and then we will call it a day. Oh, actually, I lied. It's my second to last example. 2 more examples, and then we call it a day. So, Cascadia slow slip events. Again, a ridiculously cheap analytical solution. And this is exactly the same problem as the Nile discharge problem, right? We're just going to solve for both a possible step and a possible change in rate as a function of time. But it's exactly the same problem. We're just going to do it on daily GPS solutions instead of annual discharge from the Nile River. So on this plot, the little black dots are the daily positions of various stations in the Pacific Northwest. And the blue lines are the exact same change point analysis as a function of time. What is the evidence for a step? And you see again that there is clear evidence for a step at different days on these different stations. So we're going to do a little bit of an experiment. We're going to see if I can play a movie for you. If not, we'll just give up and keep going. Hold on 1 second. Okay. Hopefully people can see this movie. And let's just play it real fast. And this is the change point for every point in time. Did people see it? Yay. Okay, so let's play that again. So every dot, so at the top you see the day changing. Actually, let's try a slow version. So at the top, you see the day changing, and each color is a probability of a change point at that station. These are stations and locations. So you can see them lighting up when they experience a step, and you can see the step propagating from south to north as the slow slip event propagates from south to north. So we have just used our little a little piecewise linear regression problem to follow along as a slow slip event propagates up the Cascadia subduction zone. And one more time for good measure, because it's fun.
Sarah, could you full screen that for us?
Sure. I think so. Is that working?
Yeah, it's better.
Okay, one more time. Okay, so let's see if we can go back to the slides we shared. Okay, and we're back, hopefully. Okay, so up to now we did a couple of examples where we found the posterior distribution numerically through Monte Carlo simulation. And then we did a couple of examples where we wrote down some math so that we could get an analytical answer for both the posterior distribution and also the evidence or the marginal likelihood. And so we could do a series of things that are just ridiculously cheap that you can just write down the answer for and you just evaluate it in a millisecond on your computer. Now we're going to look at hybrid approaches where we can mix and match because we are free to mix and match different Bayesian approaches. So actually this is what I'm working on now in my postdoc. So what I wanted to do was, for the purposes of earthquake early warning, I wanted to be able to solve for both slip models and fault geometry in real time. Now, of course, a fault geometry inversion is nonlinear, but inverting for slip on a fault with a given geometry is linear. So why not solve the linear problem analytically using a conjugate file, and then solve the fault geometry inversion with Monte Carlo simulation? And it should be pretty cheap because it's only 2 free parameters. It's the same scale as the epicenter solution problem that we did earlier. So, which brings us to our final example, real-time finite fault slip models. And this is wrapping a Monte Carlo simulation around an analytical solution. So, what we're going to do is assume that we know the location of the earthquake from an earthquake early warning algorithm. And then we're just going to plop a fault down on the location, center it on that location, and then say, but I don't know the orientation of this fault. So I'm going to solve for the strike and dip of that fault. So the fault geometry, the nonlinear part of the inversion, is just 2 free parameters. Now for each realization of strike and dip, we then evaluate the evidence for that fault geometry by once again doing the normal inverse gamma analytical linear regression solution for slip on that fault geometry. So we get the best fault geometry by maximizing the evidence, and then the slip on that fault is just given by the analytical solution. And this is exactly the same as the Nile discharge problem and the Cascadia slow slip problem. It's just instead of solving for a degree 1 or degree 2 polynomial fit, our inversion is a linear regression for all the hundreds of slip parameters describing the 2 components of slip on each of the hundreds of subfaults. But because we're using an analytical solution instead of trying to simulate them with Monte Carlo simulation, we've escaped the cost of dimensionality. And the evidence is used to find the optimal model design, but instead of the model design being, what time do I have a step in my GPS data, or what year did the annual discharge from the Nile changed, what the evidence is in favor of that strike and dip. It's basically how good was that Green's function matrix that I calculated for that strike and dip, rather than how good is this matrix with a step in it. Okay, so this is what the results for the Tohoku earthquake, and this is an inversion, a simulated inversion 300 seconds after the origin time. So the black arrows in the top plot are offsets calculated by taking the difference in the data at 300 seconds after the origin time from the positions of those same stations at the origin time. And then using those offsets as my data, I calculate the normal inverse gamma linear regression and the marginal likelihood for that model design for each of many, many different strikes and dips. And that's what we're showing in the bottom plot. The bottom plot is the color scale is giving you the log of the evidence or the log of the marginal likelihood as a function of strike and dip of the fault. And the little black diamond shows you the fault geometry that has the highest probability. So this is the most favored model. That geometry is what's plotted in the top plot. And the slip model there is the mean model from the normal inverse gamma conjugate file analytical linear regression thing. And the red arrows, which are on top of the black arrows, such as you can't really see the black arrows, are the predictions from that slip model. And the slip model estimates magnitude 8.8, which isn't bad. It's really about a magnitude 9 earthquake. So obviously, this is not a great slip model, right? This is comparing this to what we did in example 2 when we did, the full, big, kinematic rupture model, with 50 billion simulated ruptures on the big supercomputer. That's a much better analysis of the rupture model for this earthquake. But that thing took forever to calculate on a supercomputer. And this takes, a second or seconds on your desktop, because this is mostly analytical. And the Monte Carlo sampling is only over strike and dip. So you can combine the analytical and the non-analytical methods however you want. Okay, so we are coming to the end. Conclusions. So Bayesian analysis has a lot of advantages over traditional optimization solutions. It's a great way to handle underdetermined inverse problems. And we have a lot of underdetermined inverse problems in geophysics. And the reason that it's so good for underdetermined inverse problems is because it produces the ensemble of all plausible solutions. Not just a solution that satisfies the data and your regularization scheme to make the problem invertible. It's the whole solution constrained only with whatever physics you want to put into the problem, not with any kind of regularization needed to make the solution numerically stable. And given sufficient computational resources, any solution that you want to describe, linear, nonlinear, any kind of constraints, complex, simple, whatever, can be formed by, oh, it's not full screen? Uh-oh. Okay. Can be described by Monte Carlo simulations. For some problems, the solution is, now, for other, but that can be very, So you can solve any problem you want using Monte Carlo simulation. It can be computationally expensive. It may require an infinite amount of time to solve the problem numerically. Now, for some problems, you can make an analytical solution. And when you do that, the thing is computationally cheap and easy, just like doing least squares. And so this is my very, very last slide, and these are just some things to think about. So I showed like 5 different examples today, but those were just doing quick, simple inverse problems. You can do all sorts of interesting things with Bayesian analysis. So in addition, sticking with inverse problems for a second, you can include anything you like in the inverse. For example, it's encouraged in Bayesian analysis to re-estimate your errors, to say, okay, these are the uncertainties you think you have on your data, but maybe there are errors in your Green's functions. Maybe there are errors in your forward model. Maybe there are additional sources of noise that you don't know. Let's estimate those things, or re-estimate our formal errors as part of the inversion. And in that case, it's just the same problem. It's just that the vector of parameters is not just what goes into your forward model. It's that vector gets augmented by, sigma, the variance of your uncertainties, or some additional source of noise, or anything that you like. So you can solve for all sorts of things simultaneously as part of the inverse problem. It need not be just the model parameters. And certainly in the sampling setting, you're just talking about adding 1 or 2 additional variables, so it may not even make the problem much more expensive. Selecting between different model designs, as we discussed, so you don't really have to worry about statistical tests. The evidence tells you what the best model is. You don't have to come up with some statistical test that talks about how many degrees of freedom you have and how the data is. You can make probabilistic predictions of future outputs from your system. You can do machine learning. There's all sorts of classification problems you can do with Bayesian inference. There's a lot of stuff out there that we haven't even touched on. And so there are many, many, many things you can use this for. And I hope that you will find this exciting. I hope that you will consider this for your future research needs. And I hope that you will ask me lots of questions now.
Great. Thank you so much, Sarah, for your time today and sharing a technique with us that has so many applications to a wide range of problems. I see Lena's typing. If anybody else has some questions, please go ahead and type them into the chat window, and we'll answer them as they come up.
Lena asked, could you use Bayesian for forecasting volcanic eruptions? Yeah, so I think a point I would really like to emphasize is just because I kept showing examples having to do with earthquakes because I'm a seismologist, none of this knows anything about the thing that you all are modeling, right? Every equation just says you have some theta, which is a vector of parameters you are trying to make inferences about. So you can use it for any kind of problem. The question is just, how expensive is that going to be? If there's an analytical solution, it's going to be incredibly cheap. If it's a numerical solution, if it's Monte Carlo simulation, it's going to be the number of samples times the cost of the forward model. And I think I sort of had a slide about this. It's how many samples do I need to fill the solution space times how long does it take to calculate each of those forward models. And so it grows, you know, very non-linearly with the number of model parameters. So anything you can do that involves a small number of model parameters is going to be cheap. Anything you can do, anything you have a supercomputer on hand for, you can probably tackle. So, you know, maybe, Lena, if you want to talk more about your problem, you could describe something about how expensive your forecast model is to run and how many feed parameters it has, and we could, you know, think about how expensive that would be. But everything can, in theory, be solved with Bayesian parameters, the Bayesian analysis. The issue is just, will it take longer than the age of the universe to do, or something like that. Yang asked, can you recommend some good books about Bayesian methods? I'm new to this method. Thanks. Oh, that's an excellent question. Well, the next question is going to be about Albert Tarantola, and he has a number of books. They're all excellent, but I do find them a little the learning curve for them can be a little high sometimes. They can occasionally be a little opaque. The Denison book that I had on the bottom of one of my slides is pretty good, but it's, as far as I can tell, it's riddled with typos, so be careful about the equations. Rederive them for yourself. A book that I'm reading now that I'm really enjoying, but unfortunately it's a little hard to find. It's by somebody named O'Hagan. Let's see. I'm typing the name now, so bear with me. Okay. So I've just started reading this book, and I'm enjoying it a lot. It's a little hard to track down because it's actually an additional volume that they wrote to stick into an encyclopedia of statistics. So it was an old-fashioned statistics encyclopedia, Kendall's Advanced Theory of Statistics, and they said, oh, we should add a volume on Bayesian inference to it. So the volume 2B is called Bayesian Inference, and I'm enjoying that book a lot. Also, a lot of the books, I think Astor's book, some of them standard inverse methods books, the newest versions that are coming out have now sections on Bayesian analysis. There's kind of a hint in Mackey's book, but not so much. I do believe Astor's book now, the new version, which I haven't seen yet, but I think it's supposed to have a big section on Bayesian analysis. And that's Astor. And okay, so grossly, can you summarize the new developments on the method since Albert Tarantola? That's a tricky question to answer. Of course, I suppose the bigger question is whether, you know, it's funny when you go through the literature on Bayesian methods. There's obviously such a huge amount of not understanding, misunderstanding, denseness, jargonness, because you will see the same thing independently re-derived 20 years later without anyone realizing that it happened 20 years before. So one of the most famous examples of this is the Metropolis algorithm, which was published in 1954 as part of the for a statistical mechanics problem. And it wasn't until, I don't know, 10, 20 years later that people realized, hey, wait a minute, this isn't just some method that they came up with to simulate this statistical mechanics distribution that they were talking about in this paper. This is a generic method that can be used to simulate any kind of PDF. And then, so really, it's often known as Metropolis-Hastings algorithm because it wasn't until Hastings came along that people knew what the heck Metropolis was talking about. So I hate to quantify the difference between Albert's work and what happened since Albert's work because that would imply that I fully comprehend the importance and impact of Albert's work, which I'm not sure about because nobody seems to comprehend what anyone's doing. He did many important things. It's often a little opaque. I would not necessarily use it as an introductory method, but once you get into it, you will see that there are a lot of interesting and important things. But of course, he in turn is, you know, way before him were people like James, who wrote, I forget what his book is called, Probabilistic Inference, Probability Logic, the theory of something with probability and logic in it, and that is like the Bible that explains all of the theory of how you infer things based on data and files. And, you know, before him, there were people like Fox and Chow doing important things well. So, you know, it's quite possible that everything important has already been said, but I just don't understand it yet. All right, that was probably a very unhelpful answer. Are there any other questions?
That was a very helpful answer, Sarah. I get the impression that there's a lot of work that's been done on this, but no one has kind of done a comprehensive review of it. While we're waiting to see if anybody has any other questions, I want to remind people of our next webinar. Our next webinar will be May 16th. It'll be by Nick Featherstone. Nick will be talking about stellar scalable pseudospectral methods in the Geodynamo. I don't see anybody typing. This is your last chance. Okay, I think people are starting to drop off now. So thank you so much, Sarah, for coming back to us again and giving us this webinar. It was very, very informative. And oops, we got some typing. Hang on. Oh.
Well, thank you so much, everyone, for coming and for coming back a second time after the first time went all technically bad, and for sitting through the various technical issues today. And thank you so much, Lorraine, for having